Hello everyone, my name is Junosuke Suzuki at Tokyo Institute of Technology in Yokohama. In this video, I will talk about ProgressiveNN achieving computational scalability without network alteration by MSB-first accumulative computation. Here is the outline on my presentation. In recent years, DNN provide a high accuracy for a variety of tasks and are used in many applications. DNNs in edge devices have features such as low latency and real-time control. However, edge devices are constrained by power consumption and computational resources. So reducing the huge amount of computation in DNN is an important issue in edge devices. It is required to achieve the desired inference performance with lower energy consumption while satisfying the severe constraint of power consumption and computational resources. Now, I'll talk about our research purpose. Our research aims to achieve more efficient inference by adjusting the computational cost without accuracy drop. For sequential data applications such as video or audio, predicting the next result from the previous input is possible. For example, in the case of input from a video camera, if an object does not exist, this is a simple task and does not require high accuracy. In the next frame, if something is detected, we can increase the accuracy. After that, as it turned out that a person has been detected, it performs a high accuracy calculation. And then, as the object is no longer detected, it adjusts to lower accuracy again. In other words, we can use less computation for simple tasks, and we can use more computation for difficult tasks to make inference efficiently. In this way, the edge devices can adjust power consumption for task difficulty. Next, I will explain the conventional method to achieve the scalability described in the previous slide. FlexNet is one of the methods for scalable inference, and it can incrementally increase the inference cost. The unique feature of this method is that the weights are trained bit by bit from MSB. As an example, considering a 3-bit network, first, this method trains only one bit of MSB, like training binary network. After that, the train weights are fixed and it trains the next bit of the weights. Finally, by fixing trained upper 2 bits and training the LSB of the weights. This is the training process of the 3-bit weight network. This method's problem is that it requires the same training cost as much as training multiple binary networks repeatedly. Therefore, we propose a simpler method. Next, I will explain the proposed method, ProgressiveNN. ProgressiveNN is a scalable inference method and consists of 3 parts: bitwise binary quantization, batch normalization retraining, and accumulative bit serial inference. Hereafter, these are called BWB Quantization, BN retraining, and ABS inference. BWB quantization is a method proposed by FlexNet, described in the previous slide, where a single network contains a representation of multiple networks. It is an image like network A is contained in network B and network B is also contained in network C. Unlike FlexNet, our proposed method requires only a single train for multiple networks. However, compared to network C, network A and network B, which are part of network C, are less accurate than network C. So BN retraining suppresses the accuracy degradation by BWB quantization. And ABS inference adjusts the inference cost to achieve scalability utilizing BWB quantization and BN retraining. Next, I will explain BWB quantization. BWB quantization allows for a progressive numeric representation with one network weight. BWB quantization interprets 1 as plus 1 and 0 as minus 1. And BWB quantization calculated bitwise from MSB and added to the previous result. Here, we consider the 4-bit value 1010. First, looking from the MSB, the fourth digit is 1, and 1 means plus 1. In addition, considering digit alignment, plus 1 times 2 to the third power is 8, so the 1-bit value shows plus 8. Next, third digit is 0, and it means minus 1. Then the third digit is calculated to be minus 4, and in addition to the previous result, the upper 2-bit represents plus 4. Repeat this. Second digit shows plus 2, and adding plus 2 to the previous result, so third 3-bit shows plus 6, and the first digit shows minus 1, and adding minus 1 to the previous result, so the fourth 4-bit value shows plus 5. In BWB quantization, the resolution increases as the bit width increases. Considering about 4-bit value 1010 as with the previous slide, the target value is plus 5. 1-bit BWB weight can represent two values, plus 8 or minus 8. At this time, plus 8 is closer to the target value, so 1 bit shows plus 8. When it becomes 2-bit, 2-bit BWB weight represents 4 values, and plus 4 is the nearest among these 4 values. After that, the resolution gradually increases and approaches the target value. 3-bit represent plus 6 and 4-bit represent plus 5. On the other hand, there is a problem that BWB quantization has no expression for 0. However, we allow 0 weight because they are implementable as pruned weight in accelerator. Therefore, n-bit BWB quantization has to do the n plus 1 values, including 0. Next, I will explain the study, training Batchnorm and only Batchnorm. In this slide, I explain using a general residual block. First, in this study, all parameters except Bn are fixed at random initial values. After that, training only Bn with the other parameter fixed. This study reports that sufficient deep ResNet achieve high performance with training only Bn. Based on this report, we used Bn retraining in our study. Bn retraining exploits the knowledge of Bn training described in the previous slide. BWB quantization is an expression method in which the resolution gradually increases as the bit width is increased. However, there is a problem that the accuracy significantly deteriorates with the low bit BWB weights. Therefore, we used BN retraining suppress the deterioration of accuracy. BN retraining targets only the BN parameters and all other parameters are fixed. By retraining each corresponding BN for each bit width from 1 bit to n bit, accuracy can be restored with low bits. And BN use less memory than the other parameters, and only BN training is low training cost. Next, I will explain ABS inference. ABS inference is progressive inference using BWB quantization, BWB weights. Two convolutional layers in a product using BWB weights is the sum of the inner product of each bit of the weights and the corresponding input. And then, by inputting the output of the BWB weight for 1 bit to the corresponding BN, it represents a 1-bit network. And represent a 2-bit network by adding the next bit of output to the 1-bit network. By repeating this, we can represent multiple networks with a single BWB weight. ABS inference needs to calculate only the incremental portion for higher accuracy. Also, since it uses a single set of BWB weight for 1 bit to n bit networks, it can save memory usage for achieving progressive inference. In this way, ABS inference realized progressive inference using BWB quantization and BN retraining. Slide shows a summary of ProgressiveNN. ProgressiveNN consists of three parts, and BWB quantization allows for a progressive numeric representation, and BN retraining suppresses accuracy degradation with BWB quantization, and ABS inference realizes incremental inference. And ProgressiveNN has three features. First, it is similar to the usual training method. Second, ProgressiveNN applicable to already trained network as it does not require any network change. Finally, ProgressiveNN realizes scalable inference. Next, I will show the experiment results. This slide shows the experiment setting. In this experiment, we evaluate using ResNet 18 on two Shifr datasets, Shifr 10 and Shifr 100. And we adapted 8-bit VWB quantization to the weights of both of convolutional layers and fully connected layers. And we adapted 8-bit fixed point quantization to activation and the other parameters. These two figures show the accuracy on Shifr 10 and Shifr 100. The red line shows the accuracy with retraining BN for each bit width, and the blue line shows the accuracy without retraining BN. From these figures, we can confirm narrowing bit width of BWB weight degrades the accuracy. However, we can also confirm retraining BN significantly restores the accuracy with low bit. In particular, we can see the Cipher 10 has significantly improved accuracy from 1 bit to 4 bit, and on Cipher 100 has improved accuracy considerably from 1 bit to 5 bit. And accuracy of the 1 bit weight network on Cipher 10 and Cipher 100 improved to 91% and 65% respectively. Next, let's focus on the raw accuracy part of the Shifra 100. In this slide, I will show the distribution of the BWB weight These 8 figures shows the distribution of each bit width, BWB weight, in the first convolutional layer on ResNet 18. 8-bit weights in the upper left figure shows the unimodal distribution. However, we can confirm the distribution is distorted in less than 5 bits. We allow the zero representation by the weight pruned in accelerators, but the BWB does not have zero representation. So the number of zero value is always constant as the bit width narrows, and the number of relative zero decreases as the bit width gets lower. So we consider the distortion of the distribution will cause significant deterioration to accuracy. To address this problem, we focused on the expressive power of BN. Training-only BN has been reported to achieve high performance even when other parameters are frozen from random initial values. Based on this report, we considered the expressive power of BN improved raw bit accuracy. Next, I will discuss further computation reduction using activation prediction. In this slide, I explain the right figure. These 3 dots represent the activation output with the calculation of the 1-bit BWB weights, and repeat this from 1 bit to 4 bit, and then connect the dots. Each line represents the activation value of the same pixel. In this example, the two final outputs are positive and one is negative. So the red line represents the line with a final positive value, and the blue line represents the line with a final negative value. And the green circle shows the minimum of all red lines. ABS inference adjusts the computation cost by calculating each inner product value in the MSB-first order. Therefore, once the calculation with 1-bit BWB weights is over, we can predict with a high probability whether the inner product ends up with a negative or positive value in multiple bit widths. If the activation function is a real function, predicting the sign of the final value in advance can save computation cost for negative value by immediately stopping its calculation. Assuming 50% activation density on average, we can reduce 87.5% computation of the negative part and 44% of the entire calculation without accuracy degradation. This is my conclusion. In this work, we propose ProgressiveNN that enables computationally scalable inference. And the ProgressiveNN requires only a single training for multiple neural network representation. And ABS inference can satisfy this desirable inference accuracy with the minimum computation using BWB quantization and BN retraining by selecting the least bit width of weights. And we also showed that BN retraining suppresses accuracy degradation at low computation cost and restores the inference accuracy to 65% on cipher 100 at 1 bit width inference. Thank you for listening.